So hello everyone, this is lecture 37 and the last lecture for the solid state physics. In the last lecture, we were discussing about the Bragg's law and my video was muted, so I checked it. So I discussed up to here and let's start from here, that is Bragg's law. So what Bragg's law says, it is a kind of condition, means there is this planes, different planes inside a crystal. So when we get a light which scatter from it, so it can scatter from here or it can penetrate and scatter from second layer or plane, then these layers will be interfere and give us the pattern. It can be constructive or destructive, means there will be a maximum intensity or zero intensity. Okay, why? Because of this path difference, means see, this ray is reflected from here and between this second ray traveled this long path and after this it is came this side. So this distance will call the path difference between these two rays. So this path difference lead to the interference pattern or the diffraction patterns. Okay, so and we can see that if this path difference is equal to an integral multiple of lambda, then that will be our that these two rays will give us constructive interference. And if this path difference is in the form of odd integral multiple 2n plus 1 of lambda by 2, then it will give us destructive interference. Okay, so let's calculate this path difference first. So if this interplanar distance between two planes is d, if this is theta, then this will be 90 minus theta, then this angle will be again theta. So this is d, so this side will be d sine theta and this will be d sine theta. So this path difference will be 2d sine theta. And here we require only those layers where we are getting constructive interference. So only that will be required to get the information about the crystal. So 2d sine theta equal to n lambda. So this is our path difference. This should be equal to the integral multiple of lambda for the constructive interference, and it should be this multiple of this for destructive. And now see, with this path difference we can find the phase difference also. So the relation between the path difference phase difference is 2 pi by lambda multiply path difference give you phase difference. So if you put the lambda in place of path difference and n lambda, you will get phase difference as 0, 2 pi, 4 pi and all. And if you place in the place of path difference this, then you will get phase difference as pi, 3 pi, 5 pi and all. Okay, so we already discussed about this. So this is all Bragg's law. Okay, so any crystal by which we are getting the diffraction pattern, that should follow the Bragg's law. Okay, so remember this. Now let's start today's topic, that is types of XRD. X-ray diffraction we discussed it, and we discussed the planes, means different kinds of, means if inside a crystal if planes are present and not. Okay, so different planes and their middle indices we discussed. And for different kind of structures like BCC, FCC, how can we determine that which planes will be present? We read some rules, so remember those rules, they will be very helpful here now. So see, if this is our incident ray and it is making angle theta to this plane, then this theta will be this and d will be interplanar distancing and lambda will be wavelength of this ray. Okay, now there we have three methods in XRD. These are Lewis method, crystal rotating method and the powder method. So we'll get a brief idea of these two and a little bit in detail for the powder method because this is important. So let's see, just remember these. In Lewis method theta will be fixed and lambda will be variable. In crystal rotating, this variable and this fixed. In powder method, this is variable and this is fixed. So let's see first Lewis method, what it says. See this crystal first, this is a unit cell. Now inside this unit cell we can have infinite number of planes, and for different planes we have different Miller indices. Okay, so now what is in this condition is that theta will be fixed and lambda will be variable. So here is this hole, these are photographic plates, means on which we are observing the diffraction pattern, okay, from this crystal. And there is this hole, X-rays coming from this side and it will hit the plane and it will scatter, and then we will get these points and the patterns. So we will study these patterns. Let's see how. So first let's see theta is, means let's consider first this plane. So Miller indices for this plane is 110 because it is intersecting at x and y and z is infinity, so you will get 110 for this. So d110 will be a upon root h square plus k square plus l square, that is the formula. So you will get a upon root 2 here, this is d here. So from this formula, if you calculate, and theta, let's consider theta is 30 degree, okay, for this plane, then we find the lambda. So we will get the value of lambda will be 2.8 angstrom. Same if we'll consider this second plane, like this 1 1 plane will be joined this point and this point, then the plane you will get is 1 1 1, okay. So you will get this plane. So for this you have small d will be a upon root 3, okay, because a upon root h square plus k square plus l square. Now consider for theta will be 45 degree for that plane, then we will calculate the lambda. It will came out to be 3.3 angstrom. So see, for different planes we are having different wavelengths, okay. So what we will do, we will vary the wavelength from this side, and we will observe that for what wavelengths we are getting these diffraction pattern. If we are getting, means that's how we can see that which plane is present and which plane is not. Because for means, let's say we applied this wavelength from this side, then we will say that we will observe the diffraction pattern, and that will confirm the presence of this plane 1 1 1. If there is no pattern, then we will say that this plane is absent. And if we get the information that if plane is present and which planes are absent, then we can definitely know that which kind of crystal it is, because we already discussed the condition for the BCC is SC and the FCC, that which kind of planes are present there. So let's say this H represents the h square plus k square plus l square. Then for h equal to 1, we will have this Miller indices. For 2, this will be this, 3 for this, 4 for this. So let's say we are getting for all these planes, means we are getting diffraction pattern on all these planes, means these all planes will be present. And what this gives us, means what information we get if these all planes are present. So we remember the thing we discussed in the simple cubic, that all planes will be present only in the simple cubic, okay. So by getting this information, we will say that our crystal is simple cubic. Now let's see only these H are present, 2 4 6 8 10 12 14 16. So see, for 2 it will be 1 1 0, 4 it will be 2 0 0, 6 it will be 2 1 1. So see, now only those planes are present whose Miller indices sum are even. So for 2 it is 1 1 1 0, 2, total sum will be 2. For 4 it will be 2, sum will be 2. For 6, sum will be 4. So see, only those planes are present whose Miller indices sum is even. So what this condition tells us, so we remember the rule. This was the rule for the BCC, that only those planes are present whose Miller indices sum is even. So this information gives us that its structure is BCC. Now let's say these planes are present, 3 4 8 11 12. So see, for 3 this is this all odd, for 4 all even, and for 8 all are even and all odd. So we are getting planes at the unmixed. So this information gives us that the structure of the crystal is unmixed, means only the unmixed Miller indices are present. So this was the condition in the FCC. When there was mixed indices like this, odd and even, then plane is not present, and we see that this plane is not present here. So we'll say that this structure is FCC. Same you can find for the DC, diamond cubic. So these planes will be present there. So by getting the information from the experiment, you will get that which planes are present, and from that information you can find the structure, okay, determine the structure. Same you did in the crystal rotating method. In rotating method, you will put a rotor here, and it will rotate this crystal like this, and in this case we will fix the lambda, but now theta will be variable. So it will give information for different theta, that which plane is present, okay. Means now in all the conditions Bragg's law should be satisfied. So now if we put the lambda as constant, then we will get different theta and different planes. So from there we will get the information that if that plane is present or not, okay. So and again we will get this kind of information that planes are present, and we can determine the structure. So in that case, this theta will be variable and lambda will be constant. So for different planes you will get different theta, and you will see that which planes are present. Now there is this third method, that is powder method. So this is a very important method. In this process we crush the crystal into fine powder particles, means an infinite number of fine powder particles, and each particle act as a crystal. Now we will apply the X-ray on it and it will reflect. Now consider this as a parallel line. Okay, then it will go like this and this. So if it is making theta angle here, then we will see that because of vertically opposite angle, this will be also theta and this is again theta. And we put our observing apparatus here. Then for this 2 theta, we observe that it is getting in higher intensity at this point. Okay, and this, let's see, this plane is 111. So if we are getting higher intensity at this 2 theta, we will say that this plane is present. So we will observe at different theta and we will different 2 theta, and we will see that these planes will be came out to be in the picture. Means we will get the intensity spikes at these theta. Means in this axis we put the 2 theta and this axis we have intensity. So on these planes we are getting spikes, means these planes are present. Now what this gives us means we are getting that these planes are present. So these are all odds, all even, all even, all odd, all even. So this is the case only in the FCC. Means remember the rules, only the unmixed planes are present. So these are unmixed. So then we will say that from this information the structure of the crystal is FCC. Now let's say at the 1 plane for 2 theta equal to 60. Okay, what information we can get here? So 2 theta equal to 60, then theta will be 30, and from this we can find the d, and we already know the lambda, it will be constant here. So from here we can determine the value of this a, that is lattice parameter. It will be lambda over 2 sin theta root h square plus k square plus l square. Substitute the value of lambda, theta is sin 30, and you will get this. So this will be your a. Now you are also getting the information of a, that is lattice parameter, and it is very important thing. Because of different element you have different a. So this is also very helpful. So that's how these experiments works and give you the information about the crystal. Now we will discuss a much more important topic, that is reciprocal lattice. So see, as we discussed the lattice points in the today's world, okay, the simple lattice points where atoms can be present. Now there is some other space also exists, and that space is of the reciprocal lattice. Means in that space, this means let's say we have this plane and there are infinite number of planes parallel to this. So each plane can be represented by a single point in that space. So we will get again a space of that points. So that space is called a reciprocal lattice space, and each point in that is called the reciprocal lattice point. So we will see that how we can determine a point to a corresponding to a single plane in the real space. So reciprocal lattice points are represented set of a parallel planes in reciprocal space. So how to determine the lattice point for a particular plane in the reciprocal lattice? So there is this method. Draw a line from an arbitrary origin normal to the plane HKL. So first we need to draw a line from an arbitrary, taken any origin and draw a line which is normal to the plane HKL, for which you have to find the lattice point. Choose length of the line to be 1 upon DHKL. So you can find DHKL, this is nothing but a over root h square plus k square plus l square. So the end point of this line represent the plane of the Miller indices HKL. So that's how you will get the end point of that line will be your reciprocal lattice point, and it is called the reciprocal lattice point. So let's see a visual representation, then it will be more clear to you. So let's say we have this lattice and this is a unit cell. So let's take this plane first. The Miller indices of this plane are 1 0 0. Okay, so now take this as origin. So first we need to take this origin and draw a line which is perpendicular to this plane. So this will be the line, this will be our line. Now we need to place a point at the distance of 1 upon DHKL from the origin. So DHKL will be a over root h square plus k square plus l square. So a over root 1 square 0 square 0 square, it will give you a. So at 1 upon a distance from the origin, let's say here is this distance, then this point is called the reciprocal lattice point for this plane. Now same, if you take a point here somewhere, this will be in the middle of this will be parallel, and you will get the Miller indices of this plane will be 2 0 0. Okay, so for 2 0 0 you will get a lattice point somewhere here, because it will be a over 2, so it will be 2 over a. So it is 2 multiply 1 upon a. So it is 1 upon a here, then 2 upon a will be somewhere here. Then again it will be a by 3 here. Then for that plane 3 0 0 you will get this lattice point. And that's how the infinite parallel planes up to this side will give you infinite lattice points, reciprocal lattice points to this side. And same you will get for this plane and the all parallel planes to this side. And same for this plane you will get all to this side. Okay, now you are getting these lattice points. So these reciprocal lattice points makes their own space. Okay, so that space is reciprocal lattice space. Okay, now in that space we want to locate any point. So how we can locate that? So let's say for this point, this vector, we call it a star, and for this vector we call it b star, and whatever we get from this side in the z-axis we call it c star. So these a, b, c stars are something like I cap, j cap and k cap in the coordinate system. And now these Miller indices will work as their coordinates as the x, y, z. So in the real space we have x I cap plus y j cap plus z k cap. Here you will have h a star plus k b star plus l c star. So that's how this reciprocal lattice vector represents the any vector inside a reciprocal lattice. So for 1D this will be a star, b star, c star, like we have for the single axis y cap, j cap and k cap. So these works like that. So now there is this question, how you determine these a star, b star and c star. So you have these laws. Just remember these formulas. For a star you will put 2 pi, take the cross product of b dash into c dash. These are the vectors. And what are these vectors? So for different type of structures, like we say the simple cubic, BCC and the FCC, we have different primitive lattice vectors. So there is difference between non-primitive and the primitive lattice vectors. So here we will use the primitive lattice vectors. For the simple cubic, the primitive vectors are their original vectors in the ABC direction. But for the FCC and the BCC, you have different primitive vectors as non-primitive vectors. Okay, we will see about it. Just remember this. The formula, a star will be b cross c divided by a dot b cross c. This is called the volume of the unit cell. And b star will be c cross a and the same volume, and c star will be a cross b v, and a dash b dash c are primitive vectors. So let's see these primitive vectors. For simple cubic you will have a dash as ai cap, b dash as aj cap and c dash as ak cap, because all three sides are equal. And primitive unit cells are those where the atoms are present only at the 8 corners, and you will have net atom inside is 1. Okay, 1 lattice point, effective lattice point is 1. So only that unit cell is called the primitive, and the vectors corresponding to that is called the primitive vectors. Okay. Now for BCC you have an atom at the center and the 8 at the corner, so net effective atoms will be 2. So the normal vectors you take along the xyz axis won't be your primitive vectors, they will be non-primitive. So what will be the primitive vectors? So just I can visualize you, try to understand that you have 3 unit cells of BCC. Okay, at origin means take an origin. Now connect all the centered atoms of these 3 cells. All 3 cells means there is 1, there is 2 and there is this 3 coming out. So now take this as origin and connect the centers of all the centered atoms of 3. So these 3 vectors will give you the primitive unit vectors for BCC, means primitive vectors, not unit vectors. So these will be, if you just try to find the coordinates, you will get these coordinates. Just remember these formulas. You don't need to remember that thing. Okay, just whatever you need is in the question paper will be these. For BCC, primitive vector will be a by 2 I cap, j cap and minus k cap. For b dash will be a by 2, this is minus a by 2 plus a by 2 j cap plus a by 2 k cap, and c dash will be a by 2 minus a by 2 plus a by 2 k cap. So just remember these formulas, very important. For FCC, primitive vectors will be these. If you try to visualize, then if inside a unit cell, take the origin and connect all the adjacent face centered atoms, means facial atoms. So one side you will have here, and here and here. So these will be your coordinates and vectors. So these will be your primitive vectors for FCC, means all the face centered atoms. Okay, so remember these formulas for these three structures for the primitive vectors. Now you can just substitute a dash b dash here, and b dash c dash and these, so you can find the a star, b star and c star. Then you will have everything you need inside a reciprocal lattice space to locate any HKL, okay, or any plane by a point, because HKL represents a point in the reciprocal lattice. Now what kind of question can be asked? Find the reciprocal lattice vector of hexagonal lattice. So for hexagonal lattice, so we need to first find the primitive unit vectors for hexagonal lattice. They will be a dash will be root 3 by 2a plus a by 2 j cap. Just remember these formulas, they are as it is, remember them as it is. The b dash will be minus root 3 by 2a, a by 2 j cap, and c dash will be c k cap. Now use the same formulas. V star will be a star dot b star cross c star. So this is the volume in the reciprocal lattice space of the unit cell. So we will use the same formulas for here also, and you will get the a star, b star and c star. Just you need to do the cross product. Hope you guys know the how to do vectors cross product and the dot product. So just you need to do the maths and you will get the a star, b star and c star. If it is asked that find the volume in the reciprocal lattice space, so this will be your formula, a star dot b star cross c star. This is direct formula, otherwise you can find this v star from here also. Inside a normal cell, this is the volume of the unit cell, and this is the effective number of atoms. In the primitive cell, v dash will be this volume divided by n effective, means for BCC, you know, n effective is 2 and volume is a cube. And primitive cell, you know, if you find the volume of the primitive cell of the BCC structure, because there is this primitive cell exists in every kind of structures. So V dash will be volume of this divided by n effective. If it is 2, it will be 2 here. For simple cubic, see, it is 1 and this is a cube, and it is again a cube divided by 1, so it will remain same for the primitive cell also. So for simple cubic it will remain same, and V star is nothing but 2 pi whole cube divided by V dash. So just substitute this value here, and this will give you the volume this, and this term will be equal to this. So remember these formulas, very important. Remember this point also, make it note. Volume of first Brillouin zone will be equal to volume of second Brillouin zone. Means, you know, in the reciprocal lattice we draw the zones, and these zones are called the Brillouin zones, as we discussed previously in the lectures about the Brillouin zones when we were talking about the band theory and the tight bending. So we discussed the Brillouin zones. So all order of Brillouin zones have the same volume, and it will be equal to volume of the reciprocal lattice cell, that will be V star. So these volumes all will be equal. So question can be asked on the basis of this point, that all volumes are equal and will be equal to this. So remember this statement. Now sometimes it can be asked to find the A star and B star in 2D. So you don't have a formula for C here, so what you will take C as a k cap. So A is given, B is given, and you need to find A star, B star, so you will use the formula same as we discussed, but here you will put C as k cap, and then you find the A star as this and B star as C cross A, and all the formulas are same. So there is this question asked in the previous years: find the reciprocal lattice vector of a graphene lattice. So for graphene lattice, we know it is a hexagon shape, because hexagon shape we have in the graphene lattice, you have seen in the chemistry. So this is our graphene. Now we know these are A and B, these are non-primitive vectors, but to find this reciprocal lattice vector, we need to find the first primitive vector. So these two vectors are called the primitive vectors. So in graphene cell hexagon shape, these will be equal, this will be A, this will be A, this will be A, all will be A, and these angle will be equal 30-30, because this is 120 and these lengths are equal, so this will be 30-30. Now this length will be 30, this will again 30, this will 90. So from here you can find the coordinates. If this is the origin, then you can find the coordinates of this. So you can find this vector. How? Try to solve this first. So see here, this is vector and this is again second vector. So if you put this vector parallel to this, so this will be your resultant vector. So magnitude of this vector will be a square plus 2 a dot a cos this angle. This will be 60. So this will give you 2a square plus 2a square multiply cos 60. Cos 60 is 1 by 2. So it will again a square. So it will give you 3a square and under root will be root 3a. So magnitude of this vector will be root 3a. Now you can find the coordinate of this point as this angle is theta. So this will be this cos theta and this will be this sin theta. So this root 3a. So magnitude of this a dash is root 3a. Cos 30 will give you root 3 upon 2. Okay. So root 3a cos theta will be I cap because this is plus x direction. But this root 3a sin theta will be, means you can take from this angle also like this. Now this component will be, means this angle is also 30. So this sin theta is this. Means either you can take 60-degree angle here and root 3a cos 60 will be this, or you can take this 30a here and root 3a sin 30 will be this. So you can take anything, you will get the same result. And this will be in the minus, so that's why we written is minus j cap root 3a cos 60. So this will give you root 3 upon 2. It will give you 3 by 2 a I cap minus root 3 upon 2. This will be 1 upon 2. So this j cap. Now same, you can find the magnitude of this vector is root 3a and this angle is 30. So this component will be this root 3a cos 30 and this component will be root 3a sin 30 and this is plus, or both of them will be plus. So we get this 3 by 2a root 3 by 2a and both will be plus. So these are our primitive vectors for this hexagon shape. Now you have a and b, you will take c dash as k cap and you can find this reciprocal lattice vectors using the formula a star will be 2 pi b cross c divided by a dot b cross c. So that's how you can use the formula same for this also. Okay, so that's all. Here we end our this solid state physics. So try to revise these lectures again from the starting, and if you are getting any doubt then put it in the comment section and try to contact me. I will definitely resolve. Okay, and if you get anywhere something wrong then you can put it in the comment section. I will try to correct it if I am wrong somewhere. Okay, so thank you everyone.